All right, friends, how are we doing today? We hear me all right? Do I get a thumbs up? Are we good? Can we not people not hear me? They can't hear me. 1 second. Zoom can't hear me. Zoom, can you hear me? Great. Glad to hear it. Cool. All right, the one-man band continues to function. Wonderful. Well, it's a multi-man band. I have multiple person grad students that are very helpful for TAs for this. So hope we're all doing well. Today, hopefully have a little bit of fun. Okay, that we're going to try to actually employ some image classification. I think it'll be a good time. So let's pull up this here. So we've got for today 2603. We're going to actually be trying to classify a set of images. Now, actually, let me pull up just the example, just sort of whet your appetites a little bit. Okay, so let me see. Can I pull this up to here? Fantastic. All right. Today, we're going to be trying to classify images. So what we have here is a classic data set called the MNIST data set. You know, it stands for the Modified National Institute of Standards and Technology. The National Institute of Standards and Technology is a government agency in the United States. NIST, they standardize units for technology. You know, if you want to define what a kilogram is, NIST has a definition, right? Whenever there needs to be a national standard for how you weigh things. There are national standards for all kinds of things, for buildings and even for robots. There are national standardized courses for robots to go over. That way, there's a unified standard for companies and academia to test their stuff on. And now they also have a national standard for how they would test machine learning algorithms for image classification. And so this is the MNIST data set, the modified. The M stands for modified here. So we have these on the right, these sort of low resolution images. Hope you can see there, right? Okay. So you have those images, and so they look like they're hand-drawn pixel, almost like Microsoft Paint pixel versions of numbers. And we recognize them as numbers because, we have seen these before. We recognize them as numbers. But can we train a machine learning algorithm to classify these as one set of numbers? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And look, you have all different kinds of scripts, those kinds of things, right? So, how do we create a machine learning algorithm to do that? And that takes us back to what we did in class on Tuesday. We're going to create a convolutional neural network, and we're going to train it to classify these images. Now, which kind of paradigm of machine learning is this? Is it supervised, unsupervised, or reinforcement? What's the best fit for it? And the answer is supervised. Supervised because each of these images, those are our inputs, that's our X data, but they also have a label where we tell it the examples that that's a 0, that's a 1, that's a 4, that's a 0, etc. So because it's labeled and we're trying to predict labeled data, it is supervised. Okay, so it is a supervised problem, but instead of being a regression problem, we're trying to fit the curve. We are trying to classify this as one of many images. So imagine, my friends, let's go to the board. So we're going to do image classification. With a convolutional neural network. Or CNN. Okay. And we're going to go through an example. This is an example that's been modified off of Keris's examples, but we're going to be using Keris. Okay. We're going to use Keris, which is an API for TensorFlow, as you'll recall from when we did the example with the regression. Okay. So we're going to be using, of course, colab.research.google.com to do some Python coding. Okay. So that way, you can actually get it So we can train a network. So if we give it a new one of these images, one that's not in the training set, that's in the test set, it has a reasonable job of predicting what number it is. Okay? So thankfully, this is all pretty well built in to Keras. It's a very such a common example, so it shouldn't be too hard to follow along as what we're putting together. But it's going to be the same kind of process where we're going to be building a neural, we're going to build and train a neural network. Okay? We're going to be using different activation functions that we had done previously. Instead of doing our TNHs, we're going to be using things like activations such as ReLU. That's the rectified linear unit. Kind of looks like that. And something called softmax, which is more or less a maximum of a number of inputs, but it is softened. It's not as quite as hard. I'll show you what I mean. So imagine, like if you have a bunch of numbers on a bar plot, right? Here's my bar plot. Okay. Here's some Y, here's some X. Okay. What's the maximum of those bar plots, right? That's the max, right? Right. However, however, that is a hard switch that if all of a sudden this bar becomes high enough and then passes the other one, there's sort of a hard switch as to which one is the max. It completely switches off what the max is, which can be non-differentiable. Or you can soften that switch, okay? You can look up the equations for softmax, but it's basically a maximum that's easier for neural network training to deal with, okay? So we'll be using those kind of activation functions, but those will all be built in, okay? All right, so let's get started here. We're going to pull up research.google.colab.com, research.colab.research.google.com. Pull up your account, okay? Let me pull it up for me, actually. All right, research Colab, research.google.com. I'm going to pull up a new one. It's not up for you yet. I'm going to have a new notebook. Okay. All right, let me make this bigger here. Yep. Sorry, I'm trying to get this the right size so you can see it okay. Hopefully you can see that all right. Okay, we've got a new Python notebook, okay? And this one we're gonna build it from scratch, all right? And we're gonna use a lot of built-in functions within Keras to help us out. They already have the built-in data set. So let's start from scratch here. So we're gonna call, image, MNIST image classification with CNNs, convolutional neural networks, okay? You can name it whatever you want. I just gave it an absurd name here. Okay. So let's give us a little text here. So this is great. Classifying images in the MNIST dataset using convolutional neural networks, or CNNs. Okay. All right. And this is going to be by Christian Hibicki et al. Okay, but it is adapted from Keras examples. Okay. Credit where credit is due. Okay. All right. So we're going to be using things like, we're going to be using a few of the techniques that we talked about in class. So for instance, we're going to be using, let's see, can we add a little number list? We're going to be using convolutional layers. We're going to be using pooling. Okay. And we're going to be using dropout layers. Okay, it's a new thing we have not talked about before. Okay, got it. Okay, all right. So moving on with that. Give me a second if you could. My problem is the Zoom also throws off a lot of my other things. I'm going to do my best. Okay. All right. Yeah, it'll slow me down a little bit. That's all right. So let's start at the beginning here. So what I want to do is we're going to start importing our libraries. So let's start importing libraries. Okay, let's use some of our standards. We're going to import NumPy. Okay, import NumPy as NP. All right, and we're going to import matplotlib. We'll try to make best. We'll try to plot some things. Matplotlib.pyplot as PLT. Okay, we're importing those libraries. Make sure we spell them right. Anytime now. Okay. All right, but we're also going to be using TensorFlow. Okay, so we got TensorFlow. So we're going to import TensorFlow as TF. Now, we did not use TensorFlow directly. We go through an API called Keras. That's an easier way to start off. So let's include Keras as well. So import Keras. But from Keras, we're going to particularly import the layers library. Okay, because we're going to be building these networks of layers, just like we did in the past. Okay, so once we make sure we can import all these things, make sure that all works, and in fact seems to work. That is great. Okay, we're just going to go through this straight through, and we're going to start. And as we build our network, and as we try to train our network, we're going to add more and more features. Okay, so what are we going to be doing? So we are going to be doing. So let's go back to here. Okay, now let's go back. All right. So we're going to build a network. Now recall, if we're going to have images, those images are going to be our inputs. Our input. Okay. And these are going to be all the pixels. Okay. And they're going to be going into some kind of convolutional layer at some point, some kind of convolution. The reason we do that is because the convolution, the convolution is very efficient at taking in nearby pixels, okay, and not having connections across all these things, and it reduces the number of connections that we need in order to actually process the image. It more looks like nearby the pixels, the other pixels. That was the example we used last class, where I took a photo of you all and showed that if you just do very simple analyses of nearby pixels, you can start to see some patterns emerge, right? That's one of the beauties of convolutional networks, is it mostly deals with pixels that are nearby other pixels, okay? So you have a convolutional network, some kind of convolutional network. Then we go into what we call a pooling layer, a pool, okay? Remember that you might recall that's where a pool is something where you, let's say you take something that looks like this, that's like a 4x4, and then you could do something like a max pool, where it turns it into a 2x2, but inside each of these 2x2s is the maximum of each of these, right? A max pooling, okay? Well, we do pool, so you basically do a convolutional net layer, a pooling layer. You can go into more convolutional layers and pooling layers if you want. That adds more power to the network, okay? And then the last step you want to do is you want to flatten the network. You want to flatten, because you're going to have a lot of multi-dimensional data. You're going to flatten it out, okay? And then we're going to want to be able to turn it into a dense network. And that will be our output. What's going to happen at this last layer, okay, I'm running out of space here. I'm doing my best to balance everything out. So at the final layer, what we're going to want are a bunch of outputs saying, hey, this represents the number 1. This represents number 2, number 3, number 4, number 5, up to 9. And the one that is on, and all the other ones are off, or the maximum value, right? So the one that is like, if the 4, the output 4, has the highest activation value, then the answer is 4. That image that went in is the number 4. If the highest value is the one associated with the 2 output, the output's number 2. So the highest output is the predicted number. Classification. So you have 10 of those, 1 through 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe the 0 there too, right? For all those outputs, right? So that's your final layer, and that's your output. But your input is all those pixels. And as we talked about, there's a ton of pixels in an image. These are smaller images, so it's going to be a little easier to deal with. It's going to be a little easier for us to train. Okay? All right. So with that, let's get back to our MNIST example. So we've imported our libraries. Isn't that great? Isn't that swell? Okay. All right, let's move along. Back. Okay. We have the Keras library. So what we actually, the Keras library installed, and part of the Keras library, particular, is actually this MNIST data set. Okay. All right. So what we're going to do is actually load the MNIST data set. So let's make a new code block. Let's going to load the MNIST data set. Okay. And so what the MNIST data set is going to give us a training set and a test set. So the way that we actually load this in, here's the syntax. You can look up online how you load this in. Okay. We're going to create something called the X-train. We'll have the X training set. That's the input. And the Y training set, that's the output. Okay. But we can also get the test set. We'll call it X test set and the Y test set. Okay. And we're going to import from Keras this library. Now, you know from your first homework, right, that you can import data just by dragging it into the Google Colab library environment, into the environment, and you have access to that data. You can import that data just like we did in the homework. Okay. But here's one that's built in. That's a little easy. We'll say Keras dot datasets dot MNIST dot load data underscore data, open close. Okay, I'm going to run that, make sure that works here. Okay, downloading data. Oh, it downloads directly from online, of course. Okay, look, it's loading the data. It's got it there. Okay, now we have loaded that data. Isn't that nice? Isn't that grand? Okay. All right, so now I want to show you what that data looks like. These are images. So I'm going to plot these images. And again, great thank you to my TAs for helping putting together a very clean example to go off of. So let's plot example images from the data set. Okay? So let's plot them. We have matplotlib, and matplotlib does more than just plot graphs. It also plots images. Okay? So I'm going to say that, I'm going to create an image which comes from our training data set, xtrain. Okay? And it's a big array of images. I'm just going to grab the first one by indexing it like this. Okay? Now I'm going to try just plot im show for image show of my image. I'm going to say plt.show and see what happens. Look at that. What's that number look like? Kind of looks like the number 5 to me. Right? Not bad, not bad. Can I post the Google Colab code? Sure, I can. Thank you very much. Let me put Nick, I'm going to put this into the, if you're there, I'm going to put this into the Zoom chat. If you could throw it into the, actually, I can throw it into the YouTube chat as well. Everyone who's watching this live stream here can view. Actually, Nick, I can't quite have access to that. If you could put that into the YouTube live chat, that'd be great. So look at this. Thank you very much. Awesome. So look, that's one of the images. That's the first image in the set right there. Okay. Now that's the X train. That's the data. That's the input, right? What's the classification? That's the Y train. Okay. So what happens if we just say print Y train and it is the first example of Y train. What happens when we print that? Oh, the number 5. Hey, look, that looks like the number 5, doesn't it? That's just one example, right? Now we can change the image index. Let's say we'll call it. So this is we'll call this an image index. Make it 0, and we'll replace this with image index. And you at home can do this right along. If you have an internet connection, follow right along with me. Go to that link that's in the chat, by all means, and you can follow along even while I'm coding live here. Okay, image index. Oh, that's not what I wanted. Image index. If I rerun this, it should plot it 5, 5. And so I have, so it's 5. Let's grab another random index, which is say 50. Okay, 3. Oh, look at that. See? Look at those images. Now, a couple little tricks that we can do to make this a little bit more readable, and just to show an example here is we can make the gray. So what you can notice that it's got a weird color to it, like blue and yellow and green. That's because it's doing a heat map color scheme between two extremes. What we really want is a grayscale. So we can change the color map to a grayscale by saying, oh, show image, comma, CMap, which is the color map, and we can change it to single apostrophe gray. Okay, grayscale. Look at that. All right, cleaner. Doesn't have the weird heat map colors, right? So you can show it like that. Not bad, right? We can make it a little fancier looking. We can make the title the actual number. We can say plt.title. Okay, and I'm going to create a. Let's create a label. Yeah. So where's Y train? I'm gonna get rid of this print here. I'm gonna create a label. The label is equal to Y train image index. All right. I'm gonna create a little title block here. So it's gonna say, let's say, F label format label. See what happens there. There we go. This is a formatting where it says label, and then you have then it inserts into the text that you want the actual numeric value of label inside these curly brackets. That's how you can do some nice sort of inserted numbers into text for a title like that. Look, label is 3, the number is 3. I don't like those axes. Like, I guess you can see the number of pixels here. It's from 0 to about 30, 28. It's 28 by 28 image. It's not a huge image, but good for our purposes. We can turn the axes off by saying plt.axis off, single quote off. Beautiful, right? It's an example. Now we can show. So that's what the data set looks like. Okay. How many images are in the data set? Let's try it. Let's say print X train. That length, will that work? Doesn't like that. No. ND array. Yeah. We'll say that for another time. That's what I get for improvising. Here we go. That's image number 50. Let's try image 1000. Got over 1,000 images. 5,000 images. Yep, we got a lot of images there, right? That's the number 7, apparently. What monster drew that as a number 7? That's what I want to know. Okay? All right. Anyway, so we got this. Hey, Hamza, it's good to have you in the chat. I see you in the chat over there. Hope you're enjoying. Hope you had a safe flight. Okay? All right. Hamza is a great student of ours here at the college, doing great things. So anyway, now we can plot this. Let's actually start doing some neural network stuff. Okay? So back to the neural net side of things. So we've got what we need to now do. We have this data set in place. But now we need to create the actual neural network. Okay? So here we go. We're going to create the neural network. Okay? Okay. A couple of things we're going to do. One thing we're going to do is it's going to make our lives a little easier if we are all getting the same result here with me or at home. Okay? Because one thing that for all this training that we're doing, it's using not gradient descent, but a version of stochastic gradient descent. This means random, meaning it's drawing random numbers, right? Okay, so we're all drawing different random numbers, but one way to make sure that we are all drawing the same random numbers is we can set the initial random seed. We can set the random seed. So set the random seed. This is a number that randomizers use to then generate all their future numbers. They look random, but they're in fact just very hard to predict, pseudo-random. Okay, so we're going to say keras.utils for utilities, and for random seed. Okay, all right, and we can set it. I'm just going to set it to number 42. Why? Because my grad student set it to that. I'm assuming it's a Hitchhiker's Guide reference. Okay, there we go. All right. You can choose whatever random seed you want. If you want the same results as me, choose 42. All right. All right, moving on. So now we want to actually make our network. Okay. Let's make our network. Okay. So what we need to make is a model. Okay. Model is equal to keras dot sequential. This is a sequential network. It's not a recurrent network. It doesn't loop back on itself. Nothing like that. Set everything here. Just reminding you. Okay. This is a sequential network where we're going to be moving from one side to another, from input to output, that direction, right? So it's going to be a sequential network. All right, I'm going to do an open parenthesis, but then we're going to move this to the next line so we have plenty of space. All right. And to set up many layers all in a row, we're going to do a little square bracket. So this is going to be what our layer looks like. So every layer is going to be a new line. Okay. So we're going to have an input layer. Now our input layer is going to be taking in our image value, our image, which is made of a 28 by 28 pixels. Okay, right there, 28 by 28. So what's 28 squared? It's less than 900, more than 400, approximately 700 something, right? They're gonna be 700 some pixels. That's just a ballpark. So we want to make sure that we set the input to be the right size and shape. Okay. Apologies while I change the size very quickly. I want to make sure that I see everything correctly. All right. Oh, we have a few more things we got to do. I apologize. I've skipped a step here. So before we create the network, right now our image values, these pixels, their values, if it's black, it's 0. If it's white, does anyone remember what the white value was last lecture? It wasn't 1. It was 255. It is important to remember to normalize your data. So remember to normalize your data. Meaning it's best if you can put it between like -1 and 1 or 0 and 1. It helps scales the problem well. So range from 0 to 1 for all those pixel values. Okay. All right, so how can we set that? So we can rescale. So it's scale image values from 0 to 1. We can say that xtrain, thing that we already have, is equal to xtrain. And we could divide it by 255. The only problem is it's currently an integer and not a floating point value. So doing integer division will create weird results. It will automatically round to zeros and stuff like that. That's not what we want. We want a floating point value. So we're going to set it as a type. We're going to say dot as type. As type, we're going to turn it into a floating point value. Okay, float. 32 in a 32-bit float while we're at it. Okay. All right. And then we're going to divide it by 255. Okay. 255 being the maximum value. There we go. All right. And the same thing for the training set. So for the test set, I'm sorry. So xtest dot as type, set it to a float 32. There's a 32-bit floating point number, so there's enough precision there. Divided by 255. Okay. Right. All right. Now, one thing we also have to do is that the way that we need to make sure that these are the right shape. So yes, these might have a 28 by 28 amount of pixels, but are they 700 something by 1 vector, or are they a 28 by 28 matrix? We want to set it to the right shape. So we want to set images to be the right shape to be accepted by our CNN, our convolutional neural network. Okay, so we're going to say xtrain is equal to np dot expand dimensions. Okay, and so we say it's xtrain comma -1. This will set the shape to be the right shape to be accepted into our big network of pixels. Okay, we want to do the same thing for xtest. So we can say we'll just grab this and say xtest and copy it. All right, xtest and xtest. Let's run this code to make sure it's all working okay. Yeah, no errors. It's good. I like it. I like it. All right. Okay. All right. So if we then need to, fantastic. All right. If we want to print what the shape is, well, we could say, hey, what is the shape of this? Let's print, know what it is. We could say we could print xtrain dot shape 0. See what comes out. 60,000. Okay. That's the number of samples. Okay. So we have 60,000 training examples. Okay. And now the number of test data. How many test images do we have? Test number of samples, 10,000. 60,000 for training, 10,000 for test. Okay. That's the number of samples that we've got. Okay. All right. Now this normalizes all the data. Okay. Now we need to make sure that we also format the labels into a format our Keras built network can read. Okay, because right now there are a bunch of numbers. We want to make sure they're the right shape. Okay, they be read on the output. All right, so let's do y train. These are our outputs. These are our labels. It's equal to Keras dot utilities or utils And these are categorical. We're going to make sure that they are categories. Like 2 categorical. They have it as a tab complete. If you're wondering how I'm auto-completing, I'm hitting tab when those things show up that I want. 2 categorical. Let's make it Y train. Okay, that's the Y training data. And the number of classes that we have. Number of classes. Now we have 10 classes. Did we define number of classes above? Let's see. It should be 10 classes. Did I set the number of classes? I forget if I wrote it up above. I don't think I did. I don't think I did. Give me a second. This is a lot of screens to balance, so I appreciate everyone's patience. Okay. Let's see if that works. Let's see if it runs. If that's the way we'll check. Num classes. It doesn't know what num classes is. Where's num classes in my example here? Oh yeah, it's just 10. We said it's 10. That's the number of classes. There are 10 numbers that we're curious about actually of categorizing, right? So num classes equals 10. I didn't know if we had to pull it out of the data set somehow. Okay. So it turns these to categories of 10 classes. Okay. We just said number of classes equal 10. Num classes. And we do the same line. Excuse me. We do the same line. I don't know where everything went. There it is. Okay. Take the same line. I'm going to copy it and paste it for our test data. So Y test is Y test, and you turn it into a categorical format, and everything works out okay. Didn't throw any errors. Okay, it's a little larger, a little smaller. Hopefully people can still see it at that size. Okay. All right. So we have shaped the data. Okay. We're going to shape and reformat the data for use by Keras. Okay. All right. Now we can create the neural network. All right. Make the neural network, and we are going to create an input layer. That's the first thing we want to create is an input layer. So we're going to say Keras dot input. Okay. And the shape is some input shape. Okay. We do not define input shape. Where's my shape? I'm getting to put this in the right spot here. Oh, input shape. Ah, yes. Okay. Forgot to put define this up above. I skipped a line here. We need to define the input shape. Now, the input shape, we know that these are 28 by 28 images. And because they're black and white images, there's not RGB and RG and B values that we had last lecture. It's by 1. 28 by 28 by 1. So how do we set that? We say that our input shape, we say is open parenthesis 28 by 28 by 1. The tuple or tuple, that's what the curly what the circular brackets mean. Okay, this sets the shape of our images, 28 by 28, and that's fixed. Okay, make sure everything still runs correctly. That still runs correctly. All right, now we can set the input to the correct input shape. All right, that's our input layer. We pull back up. Now we have our input layer. We're then going to send it into a convolutional layer. Okay, right here. That's a convolutional layer. So let's add a convolutional layer next. Okay. So Keras input, I'm going to do a comma at the end of that line. And now the next line, I'm going to add a layer. So layers dot a 2-dimensional convolution. So capital C O N V 2D, because it's a 2-dimensional image that we're sending in. So it's going to do a convolutional operation over a 2-dimensional space. Okay. Now we're going to do the size of the convolution. Sorry, the size of the convolutional layer. We're going to say 32. Okay, 32. That's going to be the size of the layer. And we have to decide also the kernel. You'll remember, not the kernel like as in the Kentucky Fried Chicken guy. Okay, that the result of a convolution, you'll recall, some output is equal to whatever your input is convolved with some kernel. Okay, And that kernel is going to have some kind of size to it. To how big is it that's going to be the sort of performing this operation on? Like how much is it smushing that layer and trying to do stuff to that local area? Okay, and it's going to be, because it's a two-dimensional image, we're going to come with a two-dimensional kernel. Okay, so that's a kernel size underscore size equals, we have to give it the size of the kernel, we'll give it a 3 by 3. Okay, got a kernel size of 3 by 3 and a comma. Okay, all right, comma. All right, now once it goes in, we got to choose the type of activation we want on that layer. Okay, so the activation function, because the convolution replaces the simple matrix multiplication. Okay, with matrix multiplication, we did as an input to a multi-layer perceptron. The convolution replaces that. We still need an activation. Okay, activation is ReLU. Okay, so what this is, the ReLU is it's off and then it starts to turn on after a certain threshold. Okay, so let's add that. Okay, now let's do, now we got to move on to a pooling operation. Okay, so and do I need another comma? I need another comma. Excuse me. Sorry, this parenthesis needs to go. So the outer parentheses should encompass everything here. Okay, so you have 32, comma, this kernel that you define, comma, this activation you define, then comma again to move on to the next line. Okay, all right. So now you can see how we define a type of, we want some kind of layer. This is the type of layer, and then we give it inputs that tell us all the details about the layer. Okay, how many hidden units do we want on the layer, for instance, right? So, all right, now let's do some pooling. So let's do some layers, add some layers, and let's do a max pooling, just like we talked about, okay? And it's max pooling in 2D is what it's called, all right? And you can define the pool size, all right? Right now we're going to do a 2 by 2. Sorry, I want to try. I can do open pool size, pool underscore size equals a 2 by 2. All right, I think that's it. So you only decide the size of the pool, okay? Move forward from there. All right. So now we're going to do a layers. We're going to flatten it out, okay? So we're going to turn this, what is this, two-dimensional image, and we're going to flatten it into something that can then be that can be pushed into just a simple, dense simple, dense perceptron layer, like a fully connected layer, okay? So we're going to say layers dot flatten. We were dealing with images before. Now we're not dealing with images. We're flattening it out. We're about to finish, right? We're going to go flatten it out. Then we're going to go to our output. Okay? All right. So now we're going to jump to layers. This is going to be our output layer here. Be our layers dot dense. Okay? And the size of this layer is going to be the output here of this is going to be our output. So the number of neurons we need at the output is our number of classes. Looking at this, is it 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So it's num classes. That's the output. So 10. Okay? Num classes. And the activation we're going to use is because we want to know what the best thing is. Okay, what is the most likely thing we've got here? We're going to do a maximum or a softmax activation. So activation is equal to softmax. Okay. All right. And I think that should make the layer. Is that true? Did I screw something up? All right. Type kernel. Missing one argument for kernel size. Am I spelling something wrong? What did I mess up here? I'm going to send you this. Oh, there we go. EL instead of AL. Thank you very much. Shows how good my spelling is. All right. Hey, that ran. Okay. Cool. Well, it ran. It didn't do, we don't know what it did, but it didn't throw an error. But the beautiful thing about Keras is that we can view a model summary by saying model.summary. Run. Okay. All right. So you can see there's our model summary. And you can see, like, okay, we have a number of parameters, 320 parameters in the first layer. Pooling doesn't have any parameters. Flattening doesn't have any parameters, kind of flattens it out. But then you have this big, dense layer at the end, okay? 54,000 parameters, that's quite a bit, okay? What we should, but in order to reduce that number, you know how we did pooling? That pooling, my friends, will take some dense data and make it less dense like this. Maybe we should pool again. Now, if we just pool once and then pool again with nothing in the middle, you might as well have just pooled to the smaller amount to begin with. It doesn't really make any sense. But what you do in order to have in order to actually boil it down to a smaller amount of data, smaller number of parameters, effectively, is you do another convolution first. We do a convolution first, again, and then we pool again. Okay, doing 2 consecutive pools isn't super meaningful. Okay, so we can add that in. We can just add another layer. We can just copy these two. Okay, all right. In fact, that's what I'm going to do. I'm going to copy these 2 layers and put them right after that. Okay, I'm going to run it. Now, you can see that, yes, I have a fair number of parameters in my model summary, but it's not 50,000, right? It's a lot fewer. A lot fewer. Okay? So here's what we got. So, all right, we have a model. Now that we have a model, we can set it up for training and see what happens. Now, it'll probably be slow. We're going to add things after this to try to make a faster training, just because it can be pretty compute intensive, all right? But let's start with this. Okay, so we've got that. So now we're going to start training. Set up our model training. Okay, let's set our batch size. Let's do a batch of 128, okay? Powers of 2 are fun, okay? And let's only run the number of epochs, the number of training iterations that we're going to do. Let's make it small. Let's just make it 15. Okay. As you notice that when we're running things, especially when we're running new models that we're training, we don't know how well they'll work. We just set a maximum number of epochs, right? We just run it for a certain number. We don't necessarily wait for a convergence. Say, hey, this many epochs, please. All right. It's pretty common. Okay. All right. So, awesome. So now we have our epoch set. Now we're going to create the optimizer. It's going to be doing the training. Okay. All right. Let's create the optimizer. So the optimizer, we're going to build it. We have all this wonderful built-in stuff from Keras. Keras.optimizers.atom. Atom is the optimizer. Now, atom is a version of stochastic gradient descent with momentum. Very common, good. I would recommend just starting with that when you're using these libraries. Atom is a great first step approximation for running an unconstrained minimizer. Okay, and we get to set a learning rate. Now, with malice of forethought, I'm setting a learning rate to about 3 times 10 to the minus 4. So a small number. Okay, this is courtesy of like some offline guessing and checking. Okay, we can play around with this. You can play around with this afterwards. See how it affects how things are moving around. All right. So now we have to define our loss function, right? Our cost function. Same as the cost function. Loss function is the cost function. Okay. Our loss is equal to Keras. Has a lot of built-in loss functions. So Keras.losses. And we're going to create what we want to create a category-based loss. Okay. And a common one is categorical cross entropy. Okay. All right. We're going to need to talk about cross entropy and entropy measures in a future lecture. So far, we managed to do everything we're doing with machine learning without talking about probabilities and without talking about statistical mechanics and entropy. Okay. That's all right. I mean, now it is fundamental to the math of how these things work, but I think it's most valuable for people who don't have a background, who don't come in with a background in statistics or probability, to show that you can do machine learning without it. However, a lot of the language and fundamental math of machine learning talks about these things. Now, you might say entropy. You all are mechanical engineers. What does entropy mean to you? Anyone in the chat is from thermodynamics. You take thermodynamics, it has to do with, heat transfer, about engines that are running. So what is it doing here? Now, people who are familiar, well, it turns out entropy is a very powerful concept in what we call information theory. It's fascinating. Okay, so entropy was first discussed in the context of like heat and thermodynamics and the exchange of energy in real space, in engines, your refrigerator. And the idea is that the entropy of the universe it must always be increasing. It can never decrease. That's all true. But when information theory was being mathematically explored in the mid 20th century, the fundamental measures of what information means, it started to take the form of what we call the exact same mathematical form as the equations for entropy, and started to have the exact same type of conservation laws. So it was called entropy. So you're not hallucinating if you're thinking about thermodynamics, right? And this is probably a little bit of a shock if you haven't been reading some of the textbook, right? But entropy is a major component of how machine learning works. So, but we'll save that for a future lecture. Okay. All right. But cross entropy is a very common loss for categorization. Okay. So let's go for that. All right. So we have to find our loss function, and okay. And let's define some metrics for our model to report, such as like accuracy, right? Or loss. Okay. So, or accuracy. We want to know how accurate the model is. So we can actually tell it that, hey, I want metrics for my model, open bracket, okay? Keras.metrics .categorical accuracy. Open close parenthesis, comma. This sets all the parameters that we need for how we're going to optimize with what loss function and what can we report out of the solution. Okay, we're going to run that, make sure it runs, and indeed it does run. Okay, doing all right so far? Doing all right so far. Okay. All right. So let's move forward here. So now we need to compile our model. Basically, this gets it ready to optimize. Compile our model. Okay, so we say model.compile. Our loss for the model is this object we already defined. It's called loss. Okay, comma. Our optimizer for our model, we've already defined it. It's called this thing. We call it optimizer. This object called optimizer. Okay, and our metrics, they are the metrics that we defined that we called metrics. Okay, that compiles our model. All right, once we have that, we can now train the model. See what happens. I'm going to train the model. Okay, so model.fit. We're going to send in our X data. It's our X training data, and our category data, our Y train data, and our batch. We already set a batch size. Our batch size equals batch size. Our batch size we want to set equal to our batch size that we set above, right? All right, and our number of epochs, we set to the equal number of the epochs that we set above. Epochs. Okay. And All right, so we're going to create something called a validation split. Basically, it says, hey, how much of that test of that should we data should we withhold for validation? And 10%. Okay, that's what that stands for. All right. So if you run that, it should start fitting our model. Okay, so I'm going to run it. Okay, what did I mess up here? Validation split. Exception encountered. Data. Arguments received. There's some kind of error. Okay, model.fit. It's all in the model fit. On the validation split is. So we're going to try to see if we can fix this up. Okay. By the way, Nick, check your teams so you can follow. I'm giving you what just take a look at that I'm sending you over teams in case we're looking for typos that I've made. Okay, let's see. Kernel, traceback, batch size, value error, cell line model.fit. Why did that not work? X train, Y train. X train, Y train, batch size, epochs. That not work. Some kind of dimensional issue. Exception encountered when sequential.call. Invalid input shape. For the tens or 0. Okay, maybe there's some kind of something. Maybe I have to run everything. Maybe, when in doubt, maybe I forgot to run everything. Okay, run all. I forgot to run all. There's lots of things I changed up above that I didn't change down below, that I didn't rerun. So, and you can see I'm on my first epoch of 18, and you can see that it's working through all those examples. So it's like it's trying to train through all those examples, 469 of them. Okay, we got rid of the validation split. We might have to put it back in. And spoilers, we're going to want to change a couple of things about this. Right now, this is going to be pretty slow. In fact, we're probably going to want to halt this because right now it's using the CPU for all of its calculations. But so many of these calculations can be accelerated by using the graphics processing unit, the GPU. So sometimes we have access to that through Google Colab. Let's see if that's the case. All right, so I'm going to stop this right now, okay? All right, and I'm going to go up above because we have the ability closer to the top of this code to actually enable the GPU. So we're going to add some new code here. We're going to enable the GPU, all right? Okay. All right. Okay. Now what we can do is we can say we want to check for physical GPU devices. And again, they are designed for faster matrix operations. And that's what a lot of this training is doing. So it's being pretty darn slow. That'll take a long time. So let's look for our GPUs. Our GPUs is equal to TensorFlow. Yeah. Okay. Nick, you can pop into my ears, by the way. It's a little easier than me getting the text message, okay? Okay. What you can do is you can check where did I lost my spot here? Okay, my GPUs, you go tf.config.list physical devices. And you could say, I want to know if there are any GPUs. Okay. Run that code. All right. And you could say, if there are GPUs, so I'm going to print GPUs. Okay. I'm going to say, if GPUs, I'm going to print F GPU is available GPUs. Okay. Else, print GPU is not available. Hey, check the runtime settings. Nick, could you pop my ear for the runtime settings, please? Right now, I don't have the runtime settings available. Yeah. 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 Yep. So anyway, so we can accelerate this if we manage to make the GPU available, because right now it's not. All right. So EF. All right. And if you could pop on with Jacob, Jacob could probably help out with that. I mean, I don't know if if he's available right now. That'd be great. So, yep, 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 yep. For GPU. All right. Okay. There we go. So I went under. I'll show people where it was. Thank you very much. So you go under too many sessions. Okay, manage sessions. I want to get rid of. I have a lot of things on my. Okay, get rid of that one. Okay, close. All right. So you can't have too many sessions open and it'll yell at you. So I wanted to runtime. I wanted to change runtime type. And I changed this to T4 GPU. So now if I run it, manage sessions. Okay, I'm gonna get rid of your here. Okay, I'm gonna get rid of this one. Okay, I think I have too many of these. So I'm gonna run, let's try that again. Maintain now, do we have it? Okay. TF config, I have to run everything all over again. That's what happened. Gotta run all. I was probably at the exit out of the session. Importing the libraries, good. Okay, GPU is available. I've got a vGPU here. That's awesome. So now if I go down, it's running the code. Where am I right now? Am I now in the training? Okay. Yep, I'm training. Look how much faster it's training now because it's GPU enabled. All right. You had to change the runtime settings. That's all you had to do. Okay. Now it's going a lot faster. Let's see how that goes. All right. Because once it's done running, we can check to see what the loss was. Now we should all get the similar answer because the randomization should be taken out of the equation because we set the random seed. Okay. All right. Looks like it's done. So I'm going to make a new block of code. I'm going to create a score for the model. Let's say the score is the model that evaluate on the test set. So we have that model. We've already trained it. Now evaluate it on our test set, please. So X test, Y test. Okay. You can make it have less text by just saying verbose equals 0. That is a nice little feature that you can add. And you can print. It's like, hey, what is my test loss? And what that is, that's the first element of score. Okay. And I can have my test accuracy. And that's the second element of score 1. Now I'm just going to only run this. It's going to evaluate the score. And look at that. My test loss is 0.04. My test accuracy is 98.985. That's 98.5% accurate. Pretty good. Pretty good. Okay. We didn't talk about dropout layers yet, but we'll get that back to that in a second. What I'm going to instead do is I'm going to try to look at individual images and see if it can predict those. Okay. All right. All right. So if we want to make a prediction, so let's try out some specific examples to test our classification. Now, what we just did is way more rigorous, 98.5% accurate, but I want to send in an example image, right? In fact, hey, we do have an example image. It is this one right up here, this image index 5000. That's the number 7, apparently. That's a terrible one. I don't like it. Let's see if it gets number 7 right. It looks so bad. I wonder if it thinks that's a 3. I kind of think that's a 3. Let's see if it thinks that's a 3. Okay. All right. So specific examples for classification. Okay. All right. So we want to make some. We want to make some predictions. Okay. Of our model, we want to predict. Okay. Our image that we sent in. We want to make sure it's reshaped. That's, we called it image way up above in our code. That was the image with that weird looking 7. It says it's a 7, looks like a 3 to me. Image.reshape 1 by 28 by 28. Okay. Make sure that's reshaping okay. Does that work? Indeed it does. All right. Now I want to see what that predicted label is. So we say the predicted label is equal to np.argmax predictions 0. Okay, what's happening here? Okay, this is telling you the index of the maximum of all the layers that came out. Okay, so it's looking at the output of the neural network. Okay, which comes out of here, right? And it's looking for which value is the biggest. It's that one, that one, that one, that one. And whichever value is the biggest, it gives you the index 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's what the argmax does. Okay? Of predictions, that's predicted label. Now let's print it. Let's practice some fancy printing. So we're going to formatted printing where we want the predicted label is our predicted label. Let's run it. What does it think that number is, friends? It thinks it's a 7? I thought it would be a 3. It's smarter than me. How about that? Is anyone getting this? Anyone need to see any other code? Because we did it. I say we. Big help from the TAs to make sure this example worked well. Okay? Right? We could run this all again. Okay? We could, like, for instance, so what we could do is we could just try different examples. We could scattershot different examples just to see that it predicts them well, right? Let's try it even. Image 30 is also very bad. That's good to know. You're all playing around. Good, you're playing around with it. Okay? This is working pretty well. Now, the thing that we need to look, what I also recommend playing with, okay, is the network itself. Okay? Here's our network. We set that all up. Here's a network. Now, a common thing that you can add to a network like this is something called a dropout layer. Okay? That basically says, that zeroes out some inputs. It says, hey, you know, like some of these elements of the layer, they're just superfluous. They are leading to an overfit, perhaps, of the data. So a common regularization technique is to drop out a lot of those input signals to a layer. Okay, so I'll show you what a dropout layer looks like. Let me put it in here. So let me go after it'll be after the flatten, we add a dropout layer. So we'd say layers dot dropout. And this is the percentage of the signals that are just randomly dropped out. Okay? So it randomly will drop them out to make sure that your result is pretty robust to like these little signals and stuff going in. Anyway, I'm not doing a great job of explaining it right now, but I changed the dropout. Okay? All right. I'm also going to go and copy my little image. Where's my image code here? I'm going to copy it down to the bottom. So I'm going to change it. I'm going to all this stuff, this image plotting here. I'm going to copy that and put it at the bottom so I can replot the image based upon what the actual prediction is. So I'm going to copy it down here. And I'm going to say true label. And then predicted label. So, or say, we'll predicted label, colon, and that's predicted label. Okay. All right. I'm going to change the, yeah, let's run everything again. Run everything. Hopefully that works. I didn't screw up something with the syntax. Someone got it to say 3? Well, you can compare to my code. This random seeds should be the same. So I think it should work similarly. I wonder, I haven't tried it. No worries, Angela. I am fascinated. Look, I've only done this myself. I didn't do it with 30, to 70 students, and you're all going to come up with different things. Oh, my true label. Oh, it's not label. What is it? Not label. True label. That's not what I want. Okay. Oh, I got a predicted. Look, I just changed the dropout layer. It actually did worse. It thinks it's a 3, when in fact it's a 0, 1, 2, 3, 4, 5, 6, 7. Really, what I need is an argmax of this label, right? np.argmax of that label. Okay, let's run that again. Here we go. Oh, no, wait, it's 7. Predicted label 7. It does think it's a 7. I screwed something up. I must have. Because predicted label is still 7. So that's cool. All right. So we have dropout layers. You have the pooling and the convolutions. Those are what are key to these convolutional networks, particularly the convolutions, the pooling. All right. So with that, isn't that pretty cool? So what that means, if you're doing a project, right? Let's say you have a whole bunch of images. That's a cat, that's a dog, that's a cat, that's a dog. And you have a network that has 2 categories, cat and dog. You can do this very similar approach. Question is, how big of a network do you need? Do you need bigger layers? Right now I have 32 ReLU units on a layer. Okay. Do you need more than that? Do you need less than that? Okay. The more complicated your categorization problem, the more that you're going to need probably. But we got away with some fairly minimal, right? That pretty cool? That's pretty cool, right? It predicted it. I'll tell you what I'm going to do, though, is I'm going to change the image index down here. So I can just check the predictions. Oh, sir. Just real quick, I'm going to take everything at the top that defines these images. Image index, xtrain. Yeah. Image index. So right now, image index 5000. I'm going to change it to image index. Let's just say, I heard someone say 30 is weird. Let's try 50 and just run this down at the bottom. Ah, true label, predicted label 7. No. Oh, wait. I have to predict. Aha, I didn't redefine the image. That's why. It's predicting the same image. So I need to put this image stuff above the prediction. Right? Okay, that'll do it. That will do it. 3, 3. Try 500. Image number 372. What's image number 372? It's a 4. It's a 4. Pretty cool. I think that's cool. All right, that takes us to the end of our lecture. Thanks for going on that journey with me, and thank you TAs for making that possible. Fun stuff, and thanks for those who are tuning in on YouTube. It's good to have you here. Okay, we'll stop the stream right here, and I'll stick around for a couple questions from the class. Have a great one.